Alright, so we are going to continue on with chapter 10. I am still missing several labs.
Can I use one of those pairs of scissors?
For
My shoelace. To cut it off.
what's wrong with your shoelace?
It's like jacked up because these shoes are cheap. It's like all like frayed. And I just kind of want to cut it off.
Wait, 720 or whatever?
Yeah, they're off brand.
You probably have 4 pair of those.
They're nice when they're normal.
My wife probably has 20s. Well, these are Doc Martens.
Yeah,
I wear
wear your
every
Air
Friday.
Maxes.
Really? Yeah. I wear a different pair every Friday.
You do?
I've got like 85 pairs of shoes.
You should.
Sneakers.
Wear
I'm
them
a
on
shoe
Monday.
guy.
Will you wear them on
Yeah.
Monday?
I mean, how many of you have I ever noticed and said something about your shoes?
Yeah, he has.
Yeah, I'm a shoe guy. Yeah, I
Tell me
noticed a
you're
girl
shoe
walk
guy.
by earlier with that, and I'm like, I like her shoes.
I don't like these shoes.
I didn't realize they were all Silverline. Bought those shoes, but yeah, I'm a shoe guy. All right. Yeah, I have. I think last count was 85 pairs.
Holy crap.
Now you gotta understand that includes like my Doc Martens and my cowboy boots, but
That's still a lot though.
just tennis shoes I gotta have easy 50. My wife has over 100.
So you guys
She has like 30 pair of Air Maxes.
Air Maxes are nice.
Yeah, they're my favorite, my personal favorite. But I'll wear a pair tomorrow, so make sure you swing by and check them out. Okay?
I will also swim.
Alrighty, so it is 3-4 today. And I've told this joke every time, I'm not going to stop now. It's the only date on the calendar you can actually do. Yep.
That you can actually do.
Yep. You can't October 10th, but I can March 4th.
Oh my gosh. Yeah, me too. I was like,
You're welcome.
Thank you.
you can
All right.
do more.
So our objective is going to be able to calculate half-life and identify units of radiation. Now, I'm going to be honest. I have been disappointed in this textbook in the past. Never more than I am with this section. Okay? And that is because, does anybody know anything about half-life? What do you know about it, Evans?
It's the rate of decay. So say you have a radioactive isotope with half-life of 30 days. Every 30 days, the amount of that isotope is going to cut in half because it's just going to decay away.
Okay.
Isn't that why they can't, like, radioactive waste can never fully go away?
Okay, because there's always going to be, no matter what, I'm just cutting it in half. You're right. England, what was yours?
Yeah, pretty much what Evan said.
Okay.
Just kind of.
Now, the problem I have is that half-life is like interest rate, right? It's just going the opposite way, right? And we have all kinds of great equations. I'm sure some of you are familiar with PERT, P-E to the R-T, right? And there's all these great equations, and the problem is they don't use any of them. They teach these as though I'm teaching 7th graders.
That's awesome.
You just use fractions?
We got like a private conversation going on over there, or oh, sticky notes. Oh, okay. Say it louder, England.
Are they just going to use the fractions then?
And it's stupid. Tell me it's not. I know a math guy.
Is his name on the wall?
Actually, his name is on the wall. Yeah. Now, so if I were just going to say half-life, and I wanted to think regular textbook definition, it is the time required for 1/2 of the sample to decay. Now, I'm telling you, this is like the dumbest, easiest way they could possibly, and maybe that's why they do it. That way you don't have to be really good at exponents or exponential equations to answer these. So, given a sample, and I missed my M there for some reason, given a sample of 28 grams with a half-life of 7 years, okay, how long will it take to have 3.5 grams left? Okay. Now, this is literally what they do. And I don't care which way you do this, because to divide by 2 is the exact same thing as if I multiplied by a half. But this is what they do. They say, well, we're starting with 28 grams, right? And I'm simply going to divide that by 2, and I'm going to get 14, right? I'm going to divide that by 2, and I'm going to get 7. And I'm going to divide that by 2, and I'm going to get 3.5, right? Which is what I wanted, 3.5 grams, correct? How many half-lives did I go through?
3.
I went through 1, 2, 3, right? So, I simply do what?
3 times.
Yeah, I take my 3 half-lives. I almost wrote files. Swap the F and the L. 3 half-lives times 7 years equals 21 years. And that is how they teach this.
That is so
Yeah, stupid. You're right.
Like, what if...
Okay, so now so this is the great question, and this is I don't know, they were sitting right there, I think, right where Ashley's sitting. By the way, good luck tonight. I'll be there to support you. The problem with teaching it this way is what?
You can't find the exact amounts out there.
Yeah, all the numbers are going to be massaged to be perfect. Does that make sense? Like, they won't ask you to find something that doesn't come out evenly. So I can't say 2.5 half-lives.
Or like
It's either 2 half-lives or it's 3 half-lives, because they don't teach you how to do it the real way. And so, kind of stupid. But I didn't write the book, so whatever.
What if they want you to find the amount of sample that's left after 9.5 years? Like,
Then guess what its half-life is going to be? Either 9.5 or 4.75 or something that works into that perfectly. Do you have a question? Or so that wasn't. You even had to pull your mask down to tell.
I had to mouth something to him real quick.
Oh, you had to mouth something to him really
I can't
quick.
do that with a mask on.
Oh,
I'm bad at reading.
yeah, that would be really hard for say, read my lips, right? All right, so let's say I think along those lines, Evan. So let's say I did this. Suppose you have 276 grams of a radioactive substance. Okay. With a half-life of 9 years. Okay. How long will it take to have 1/16 of it left? And that will be like 1/16, of the sample or whatever. Okay. Now, it doesn't say how much am I going to have left. It wants to know just 1/16 of whatever it is, right? Well, to have 1/16 of that, what is 1/16 really?
2 to the 4th.
2 to the 4th is 1 over 2. So it is 1/2 to the 4th power. Is that what you're telling me? Okay. Well, what is this number then?
It's your amount of half-life.
Yeah, that number right there is the number of half-lives, right? So, I've gone through 4 half-lives to have 1/16 of what I started with, right? But the question said, how long will it take? What am I going to do? 4 times 9, and that's going to be 36 years. Which is why I say all the numbers are going to have to work out evenly for that to work.
So if you get a weird, funky number, it's going to be wrong.
Yeah, kind of a dead giveaway. If I get some ugly number, I probably screwed something up. You know what I'm saying? So let's say I did this. So suppose you have, bless you, 28 grams left of a sample. Okay? With a half-life of 16 years. Okay? If it has gone through 5 half-lives, how much did it start with? Okay. Now, what are we kind of doing here? Yeah, we're kind of working backwards, right? So how am I going to figure out how much I started with if I only have how much is left? What? I could, but we've already proven that. Are they really going to price?
Can't you just multiply it by 2 5 times?
Say that again?
Can't you just multiply it by 2 5 times?
So you're telling me I can go 28 times 2, and that's going to give me 56, right?
Yeah.
And that would be 1 half-life, right?
So you just do
I'm going to times that by 2, and I'm going to get 112. Times that by 2, and I'm going to get 224. Times 2 is 448. Times 2 is
896.
896. So I must have started, so if we're thinking Price's way, I must have started with the 896 grams. Is that correct?
Yep.
Okay, and I could do that. Okay, now, the if you're thinking algebraically, yeah, I would say I probably would have just went 28 times 2, because we're doing the inverse of half-life, right? Times 2 raised to the 5th power. And if I look at this, I got 1, 2, 3, 4, 5. If you punch that into your calculator just like that, guess what you get?
896.
896 grams. So, does it really matter? No, I would say this is probably faster, yeah? I don't care how you do it. But that is literally how they teach this topic. Which, going back to what Evan said, if I get an ugly number, I have probably made a mistake somewhere. And that is, like I said, the most disappointing part of this chapter. Really, the most disappointing part of this entire book is they don't truly look at this as though you would as a scientist. No scientist is going to have numbers work like that. It just ain't going to happen. Yeah, England.
How would you do?
You'd use PERT.
Okay.
Yeah. It's the same type of equation. It's just a little bit different. I shouldn't say you'd use PERT. You would use an equation like PERT. And I'm going to be honest, not going to do it. Why muddy the water? We need victories this chapter. Victories after victory after victory. So, the math teacher in me says, yeah, buddy, let's do it. The chemistry teacher says, yeah, we're not going to do that. So, sorry, math teacher. And I was like, I'm cool.
Yeah, I'm good with that.
So, okay. Alrighty, now, the next part of the objective said we need to talk about what? Units of radiation, right? Now, units of radiation. This is literally just like any other kind of unit. Other than it's not based on the metric system, which means what?
It's not increments of
Yeah, it's not increments of 10, which sucks. Okay, you do need to know the most basic one is called a becquerel. Becquerel. It's called a becquerel, and this is the SI unit for radiation. Okay, now the equation for becquerel is 1, and it's weird, but then when they write becquerel, they don't capitalize it. which I find really odd because when they abbreviate it, they go 1BQ. And to me, a becquerel would be a proper name because it's the name of a type of radiation, but whatever. 1 becquerel is simply equal to 1 disintegration per second. Now, that is the SI unit. That's what everything will boil down to in some way, shape, or form. Now, what they do is they say, okay, now let's compare that to other units of radiation. Okay? Another common unit of radiation is called the Curie. C-U-R-I-E, named after Madame Curie, right? Probably foremost, explorer, discoverer of radiation, right? Probably one of the first to also what? Die from it.
There's still radiation.
Probably not the first to die from it, just the first one that we knew. Do you know what I'm saying? So there's probably other people that stumbled upon something radioactive and ultimately died. But as far as a researcher, first scientist, yeah, I mean, she's credited with kind of being the mother of modern day radioactive studies. So kind of cool. Which is also why she has an element named after named curium, which I think would be way cool.
So that's all you gotta do.
Well, yeah,
Die.
probably not going there, but it would be cool to have dentonium. I'm just saying. Maybe one of these
It
days.
does have a nice ring.
It does have a nice ring to it. Okay? What?
They have one named after like Tennessee. We can get one named
Yeah, it's funny, but I'm pretty sure.
There's an American one.
Yeah, well, like there's berkelium. I'm going to assume that stuff was not discovered, but synthesized, or, they went to the Large Hadron and made it. And Tennesseeum, I'm guessing, was by students from UT, the University of Tennessee. Berkelium was probably kids from UC Berkeley, Californium could have been kids from Cal. Somebody's doing their master or their doctorate. But it would be cool to have dentonium. Now, Curie is abbreviated CI, and the conversion factor is 1 CI is equal to 3.7 times 10 to the 10th becquerels. What does that tell you about a becquerel?
It's not very small.
Yeah, say it louder.
It's very small.
It's very small. It's a very small unit of measure. I mean, it's like millimeter compared to kilometer type stuff, right? Now, even smaller than that, but it's tiny, okay? Now, you do need to know, they go curies. They will also talk about millicuries and this symbol. Anybody remember what this fancy U-looking thing was? Micro, right? Does anybody? So if Curie was 1, what would millicuries be?
100.
So, well, if I look at it this way, if I go 1 Curie is equal to how many millicuries? 1,000 millicuries, and 1 Curie is equal to 1,000,000 microcuries. So the difference between millicurie and microcurie is what? Is 10 to the third. It's by a factor of 1,000, right? And that's something they'll look at. And it's also kind of interesting, but you talk about the SI system, everything's a factor of 10, right? And then you talk about the standard system, where everything's a factor of what? Whatever, right? That's kind of the radioactive system. Yes.
So does that mean like a millicurie is 3.7 times 10 to the 7 becquerels? Because it's smaller.
That's exactly what that means.
Could you scoot your paper?
Yeah.
Thank you.
Okay. So yeah, that would be a way to look at that price. Okay. Now, so just make sure we understand that. And then basically, if I were to write these down, I would say that 1 millicurie is equal to what? What did we say here? 1,000 microcuries, right? Because it's 10 to the third. All right. Now, going back to the fact that radiation is like standard standard system, right? We also will have what's called a RAD. Okay, RAD is radiation absorbed dose. And then you have a RAM. Has anybody ever heard the term RADs before?
Yes.
Yeah? Where?
Fallout.
From movies and videos.
From movies?
They talk about it in like paranormal shows.
I don't know. Do they?
I don't know.
Anybody? You want?
A lot more.
Do you want to know where I remember RAD the most recent? Sam Witwicky. Does anybody know who Sam Witwicky is?
Yeah,
Transformers. Who's seen the Transformers shows? When they go to his house,
When the friggin'
the Sector 7 dudes,
they're like-
6.4 rads, tag them and bag them.
Yeah,
Yeah, that's what he says. I don't remember the number, but he talks about rads because it's a unit of radiation. Because obviously the Transformers ran on probably mini nuclear reactors. So kind of cool, like a submarine. Okay, and then a RAM is radiation equivalent for man. Okay, and it's interesting, but the RAM, this is what is used in the medical field, thus the equivalent for man. Not a big deal, but one thing I did want to show you is these have like technical definitions, but I'm going to be honest, not a huge part other than to know what they are. It's like a rad is right here is the amount of radiation absorbed by 1 gram of a substance. The amount of energy absorbed varies with both the nature of the substance and the type of radiation. And then a RAM,
So it's not a constant unit.
exactly, it's not. That's why it's like, okay, whatever. Depends on what you're talking about, right? But a RAM is the amount of radiation that also factors in its energy and potential to damage tissue, which is why the RAM is what they use in the medical field, 'cause we're talking about living tissue, right? And then it says using RAM as a measure of radiation, 1 RAM of any type of radiation produces the same amount of tissue damage. So if it's a higher form of energy, then its REM's going to change. So it's kind of interesting. Doesn't make a big deal about it, but you do need to know 2 others, and they are grays. It's called a gray, and it's called a sievert. And I believe one of these is on the Learn Smarts. Yo,
So when you said 6.4 rads, so if it's like in a person, would it be different if it's like 6.4 rads in like a dog?
it would be, yeah. And so what they do, well, not in a dog, like a plant would be different. It's like what they did is they were actually scanning the plants in front of the house when they did that. Okay, so a rad in a plant would be different than a rad in a human because they're not the same kind of tissue or organisms, if you will. That's why, I'm going to be honest, I don't spend a ton of time with these because they're not, unless I'm working in a nuclear reactor or I'm working in a fallout, you know what I'm saying? It's going to be different. RAM, though, that's uniform for anything living. So if I'm at the hospital, and we're talking about any living tissue, they're going to use the RAM because then it's universal across all living tissues. Okay? Now, a gray is basically 100 rads, and a sievert is 100 REMs. So this would be just a way to change your units as far as, instead of being a huge number, I can make it a little smaller and convert it to grays. Yeah, different. Yeah, exactly. No, 100. Centa, right? Meter, centimeter.
Yep.
That's 100. So it would vary. You're right. It would change a little bit depending. Yeah. Deci's, no. Yeah, it'd have to be centa. Something like that. But again, not a big deal. You just need to know what they are. Know that RAM is the medical one. Yeah, there's nothing too complicated there on the test. Okay. Now, here's a question. Okay, so you're given 3 cookies, with one made of alpha particles, one made of beta particles, and one made of gamma rays. Where would they go if you've got a pocket, a stomach, and a lead box? Where would you put which one?
Is that what?
What?
Like alpha is in pocket, beta is in stomach.
I don't know. I'm asking.
That's my guess.
Why?
Because like we talked about like gamma particles are able to.
Whoa. Somebody tell me what's wrong with what she just said.
Gamma rays.
Yeah, not gamma particles. That's important, though, right? So gamma rays, what were you saying again?
Like we talked about it in like, and that's why we have lead boxes.
Yeah.
Like the gamma rays.
Okay.
They're like rays, they can't get through.
So gamma's going in the lead box. Okay. Now, what about the other 2?
So
Yo.
alpha is like more. It has a lot of mass, so it would stay in your pocket.
Yeah, my pocket would stop it probably because you're right. It has that mass, and it's going to have a tough time getting through. So why would I swallow the beta?
Well, it's a negative particle, right?
Yeah. But it's still radiation, right?
Well, it's the only option. Like,
You're right, it is. And the logic is it's going to get in there. Even if I put it in my pocket, my pants, the fabric, my skin ain't going to stop it anyway. So I might as well just swallow it anyway. Does that make sense? Whereas the alpha, I don't need to because my pants would protect me from that.
Can you imagine what those would taste like? Those are made in
You know,
China.
I'm gonna be honest.
Well, it tastes like you.
I don't think you'd taste it.
Well, the alpha. Would,
What?
Have you ever drank a Monster?
I've had a few.
Well, I was just saying, like, you know,
Oh,
what does
gotcha.
it taste like?
Oh yeah, I don't know. I mean, I would say, you know, it's still a cookie. It's just I don't know. You know, for me it'd be like, I don't know, oatmeal raisin or pumpkin chocolate chip. They're probably 2 of my favorites. You know.
the alpha would just be like swallowing.
Whoa, it's probably what?
Black licorice.
Oh man, I'm okay with that. You don't like black licorice?
I don't either.
Who in here likes black licorice?
Would it be probably?
What? Only 2 of us?
I'll eat it. I know it's not my favorite.
Oh, it's my favorite.
Ew.
Yeah, especially if you go to Smith and Edwards and get that good kookaburra or whatever. Yeah, I love that stuff. Alrighty, so now the next thing is fruit. Okay? Now, let's say I work in an orchard in California and I'm picking whatever the fruit is. Doesn't matter. Okay? And that fruit goes to market. What happens between the farm and market? Does anybody know? They clean it, right? What else do they do?
They put the stickers on it.
Okay, so who was that? Okay, what do they use? Why?
Doesn't it like kill all the bacteria?
I get the learn.
Okay, it does. It's used to kill bacteria. That's why they do it. That's why, like my Mason loves those little Gosner packages of milk. Anybody else like them, right?
Yeah.
Well, they'll last on the shelf for months. Yet you leave milk out on the counter for a day and it's ruined. Why is that?
There's nothing living in it.
Because the milk in the Gosner's box has been thoroughly killed of all bacteria, right? Well, how do they do that? They can't put chemicals in it because you're going to drink it, right? So they do this. Now, what were you going to say? You did the Learn Smart?
Yeah, I did the
What did it say?
It said that like it's able to disrupt the like living cells, but since the fruit is like dead, you know, like it's no longer alive and next to the tree, it doesn't like harm the fruit.
Okay, but then why don't so Howes, you said it's gamma, right?
Yeah.
So why is it gamma and not, because gamma's nasty, right? Why is it gamma and not alpha?
Well, gamma's not like a particle, so it won't like damage the fruit and all. It's just like
You're only partially right, but that's really not why they use alpha. Anybody know? Yes.
It wouldn't go through.
Probably not. You're right. But if I use alpha, where would that alpha end up?
Like eating fruit.
In the fruit. And then what's going to happen?
You're gonna eat.
Then I'm going to eat that fruit. And then that alpha particle is going to be where?
In your body.
In me. And then it's going to give me cancer.
Or radiation.
Right? Yeah, or radiation sickness. And then I'm going to get a tumor. And how are they going to kill that tumor?
With radiation.
With radiation. Explain that shit to me. I mean, tell me. It's like I'm going to cure you with what made you sick.
Yes.
Now, let me share with you a brief story. I have a cousin. I don't know. I said 5'8" earlier. He might be 5'9". He weighed about 450, right? And he went on. He enrolled to be on The Biggest Loser. Do you guys remember that show they used to do? And we thought, this is perfect. And apparently they put you through more tests than you can possibly imagine. They don't want you to get on there and then be working you out and having you have a heart attack or something, right? And so as my cousin's going through this, they discovered a tumor the size of a watermelon in his abdominal cavity. I think they said it was 28 pounds. Yeah. So something that big that is kind of wrapped around, they have a tough time just going in and cutting out because it kind of gets everywhere, right? Does anybody know what they do?
They have like different like levels of radiation.
No.
So they like have to like isolate it. So they have like several different.
They seed it. Okay? Now this is interesting. What, Gloria?
This is in the Lawrence Farm.
Oh, weird that I would teach that. Yeah, you're welcome. So what they do is they go in and they cut the tumor open and they put the seed directly in the center. And that seed is radioactive. And something that's radioactive emits it in a 360 degrees direction, right? And as it emits that radiation, what does it do to the cells of that tumor? Kills them. So what does the tumor ultimately start to do? It shrinks and it kind of pulls itself out of those nooks and crannies inside your body. And they shrunk it down till they could go in and cut it out. That's like straight up fact medical science right there. Yes.
How does it like not go like?
Okay, so here's and you gotta understand that you guys know what chemo is, right?
Yeah.
Chemo makes you violently what? Why? Because it doesn't just kill the cancer, it kills everything. Seeding kills just what's around it. What they'll do is the reason they need to put it in the middle is because it kills from the inside out. What they're hoping is that the tumor absorbs more of it before it can get outside that tumor and do damage to the rest of your cell. And then it shrinks, and then they go in and cut it out. That's why.
Why don't they do that instead of chemo?
Depending. So there's different kinds of tumors. If I've got a globule tumor called you would have to ask me that question. I don't know, but it has a name. Then they can do that. But if it's the other kind that are like a spider web, then they can't because it really doesn't have a center. So there is a difference depending on the kind of cancer it is going to depend on how I'm going to go about it. If it's the other, like a spider web, then they just put it in your body. And then they hope that they kill most of the cancer cells before they kill all of your healthy cells. And that's why chemo makes you sick. Is because they're not just killing the cancer cells, they're killing all your cells. Yes?
So when you have the radioactive seed in you, like, does it like affect you much? Or just...
It didn't him a ton because what happens is that it just damages what's around it. And as it releases that radiation, they're hoping that it's like shooting a bullet, right? That bullet gets absorbed by the cancer cells before it gets to the edge of the cancer and can damage the living cells in your body. He said that, some days he felt better than others, but it literally, I'm going to assume, when they cut it out, it was 28, I think. It started out much bigger. Yeah.
So if you left that radioactive seed in it, would it eventually shrink to the point where it would start expanding past that and then
Okay,
start damaging?
it would. So what would happen is this, and that would depend on what I put in there, and that's what you got to understand. It goes back to the half-life question. Let's say I want this. Let's say I do the math and I say I think we can get this down in 100 days, right? So I'm going to put the right amount of substance in there so that at those 100 days, it's gone through enough half-life that it's no longer going to be toxic. You know what I'm saying? So then as it does shrink, there's so little of it left in that pill that when we do go and take it out, it's not killed anything else. the math behind it's really cool, and then it's how much they put in there. And I mean, here's an example of how big they are. Look how tiny. That's what those are. They're seeds. Yeah, tiny seeds shown next to a penny. And that's what they would put inside it, and that's what they would insert inside that tumor. Just one of those. Yeah. Then it kills it from the inside out. But this, you'll see it in a lot of, there's several medical things where they would use that situation. And, I mean, there's a lot of math involved behind that to say, okay, this is the size of the tumor. This is what we want to do with it. What do I got to put in there so that is not going to do other damage to the rest of the body? What? An oncologist. Aren't they cancer doctors? I'm pretty sure that's what they're called.
So how long do they?
Hey Siri, what's an oncologist? I don't want to lead you astray.
Oncology is a branch of medicine that deals with the prevention, diagnosis, and treatment of cancer. Do you want me to?
No. There was a hand over here somewhere. Yo, house.
So would that only work with benign tumors? Because normal cancer cells would just like multiply?
Okay, so no, actually it doesn't. And what they hope is that they kill them faster than they replicate. And what they will do is they'll take a scan, they'll seed it, come back in 2 weeks, take another scan, compare the scans. If it's getting bigger, they're just going to immediately go in and do what? Try to cut it out. If it's not, then they'll let it work till it's manageable and then go in and cut it out. Yes, you're talking malign malignant or benign malignant, right? Yeah, and it just depends on what kind it is. So, you know, it's you know, I mean, it's awesome on one hand that we have that technology, but in the same token, it sucks because, let's face it, cancer kills a lot of people. Yeah.
How long did it take for your cousin to, like...
You know, I don't remember. I would say, because we found out, it's like we're the same age, and we grew up together, and I would say we found out probably from start to finish 6 months. From the time they realized what it was, sent him home, got him to a doctor, seeded it, cut it out, was probably 6 months. Yeah. But you know, it's just it was, you know, it's crazy to think back at that. I'm like, wow, the science behind that's freaking awesome. You know, which is probably why I love chemistry so much. You know, yeah.
If you use like a radioactive seed, would it be like scary for like military use?
Well, there's lots of there's lots of uses. I mean, you know, you talk about, you know, it's like and I don't want to confuse the point, but you look at all those sci-fi movies. I mean, a lot of that stuff is rooted somewhere, right? It's just like when we talked about, I don't know, we talked about Iron Man in here. Like in Iron Man, I think it was 2 where he built that.
Oh yeah.
He built the yeah. I mean, we talked about that. That's the same. I mean, that's fact. Obviously, you're not going to build one in your basement, but the science behind that is the stuff we're talking about. That is factual science, you know. And so when you start to get into the medical field, there's a ton of applications. You're right. For every medical application there's probably a military application as well. Yeah.
So like where do they find like radioactive material?
You dig it out of the ground in Moab. No one knows that story.
Oh my god, do they have to do with the boots? There's that famous like, dude, there's this statue or something in some like museum down there of this guy, and it's like a pair of like gilded boots.
Probably.
Work boots. Anyway, he was one of the first people to find like radioactive material.
Yeah, that's him. That's the guy. It's crazy. The story behind that is even better.
So, like the different radioactive isotopes, how do you make an isotope?
You don't make it.
So how
You make the green ones. The rest are discovered. So here's the best version of the story. There's a guy, just when radioactivity started to come out, guys prospected for it because they didn't realize the dangers it was. So like you talk about the gold rush, right? There was a radioactive rush. Guys in southern Utah were big, right? So there's a homeless dude. I don't know if he was homeless, but a prospector, down to his last dime, talks a local Moab guy into sponsoring him. A month later, he finds uranium in Moab. Okay, they had a uranium mine, mined it for years. Problem is that in doing so, in the early days, they didn't realize it. They mined all that dirt, piled it up right next to what? The Colorado River. Every time it would rain, where did all that radioactive waste end up? Right in the river, ended up in L.A. So about 20 years ago, they declared it what's called a Superfund site. You guys aren't old enough to even know any of this stuff. But what that is that the federal government had to come in and clean it up. Because over time, it would have all, by the time the rains, it all ended up in L.A. Because they're the biggest user of the Colorado River at that point, right? So what happens is they literally came in and they built a rail line from Moab to the middle of the desert, north of Moab. And they literally moved all that dirt that was contaminated and stuck it in a hole in the middle of nowhere out in the desert. Yeah, kind of crazy. But that guy is the guy you're talking about. Yes?
So, like, hypothetically, if, like, you went there to the random dirt in the desert, what would happen?
At this point, they've encapsulated it.
Oh, okay.
So if you had a Geiger counter, does anybody know what a Geiger counter is? A little machine that goes tick, 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 tick. When it starts to buzz, you know you're in trouble. You would probably still be able to pick up radiation coming out of the ground, but not enough that it would damage you or they wouldn't let it be. Same thing out in the West Desert, out in the Ghost Chute. You know, it's the same idea. They're encapsulating it. Would you be able to pick it up? Yes. If you were to work there, you would wear protective gear. But if you were just there for an hour, it wouldn't be a big deal. House.
So isn't, like, the situation with the Colorado River, isn't that kind of similar to, like, when they're, like, nuclear testing?
Yeah, it's the exact same stuff. The whole downwind thing. You know, when they blew up, when they tested those bombs in the West Desert, and all that dust blew to St. George, it is the exact same. We did not know. And that's what any new science, they don't know enough about when they start doing those tests. There's a video about like the first couple of tests they did out in the Atlantic. What they did is they took a boat, filled it full of pigs, and literally parked it next to the boat that they detonated. The images are still burned in my mind of what that looked like. Now imagine the dudes that worked at the power plant at Chernobyl when it melted down. We're talking brutal images. Because we just didn't understand what that radiation did. You know, nowadays, man, they take every imaginable precaution. That's why they say, you know, nobody's going to live there for 500 years. You think, hey, by then, we've got it. You know what I'm saying? But it really is kind of amazing.
So, like, if you look at, like, the bombings in, like, World War II in Japan, like,
Yeah.
how do they deal with something like that?
So you take our tax dollars and you go rebuild it.
Well, I mean, like, how do they get rid of
They
it?
don't.
Just
They
take a
don't.
couple generations for them.
Yeah, it takes years and years and years. It's just like the tsunami. Do you guys remember the tsunami that hit Japan?
Oh, like Fukushima?
I don't know, it's 10 years ago probably now. Okay, well, so it flooded a nuclear power plant. Well, when it flooded, it got into the water, right? So all that water that went back out to sea was now radioactive, it was contaminated, right? There was a barge, just like a big barge, that washed up in Alaska that was radioactive now. Because it was from Japan. It was in the tsunami, went inland, washed back out to sea, floated across the ocean, ended up in Alaska, Geiger counter, bam, it's radioactive. But it just takes some of that, there's nothing you can do, like Japan. You talk about like Nagasaki and Hiroshima, right? It took years, and I'll bet you there's still places there that you could take a Geiger counter and detect radiation just from what's left from the original bombs. You still can? Okay. I mean, it's literally just like Godzilla. I mean, they were protecting, but that's what they do. You know, there's nothing you can do to speed up the process. They just don't let anybody go there. Yes?
So there's no technology we can create to get rid of it?
We don't have it yet.
That's the scary
And
part about nuclear weapons.
You don't know. Yeah,
It's
you
that
just don't know.
even simple-
There's a reason we haven't dropped another one. I mean, there's a reason.
Yes.
Because of the devastation and the lingering effects. You know, the nuclear winter and things like that. You just don't get it. Yeah.
So, like, uranium-235.
Yes.
So you just have to find that?
Yeah. Yeah, you mine it. Now, they will. So, there are a couple processes. There's one called enrichment, where you refine it and you kind of kick it up a notch. And that's when countries get in trouble. Like, you know, like Iran, right? Okay, they built an enrichment facility. They didn't build bombs. They built an enrichment facility. Well, why was that a problem? Because the enriched uranium is what then they use to build a bomb. And if they don't have an enrichment facility, they'll never have a bomb. So yeah, that kind of thing, you're right. I mine it, I enrich it, then we go from there. Yes?
So like with that tsunami with like the infected water, is that like killing a ton of sea life?
Oh yeah, yeah, it had to have. The only problem is that it would have been immediate, early as the high concentration. Think about how big the ocean is. By the time it's been there a week or two, now that radiation has been spread out so much that the damage is probably not significant enough that you can't recover from. But I would imagine there were lots of deformed sea life within the next months after that. Yes.
So wait, by like a nuclear winter, what do you mean?
Okay, so in a nuclear winter is when you drop a bomb. Okay, it's like has anybody seen Deep Impact? Okay, an asteroid hits off the coast of like Florida or something, right? The ash cloud that is kicked up from the dust and the dirt will literally darken the sky. The sun couldn't get through. It would be just like it was winter. That's what's called a nuclear winter. And anything we were to use now would be destructive like that because our bombs are better. You know, but because they're better, it actually makes them worse. So it's kind of crazy, but that's what had happened. Yes.
So radiation causes cancer by mutating cells. Why
Now you got to understand there's a lot of little nuances in there, but what happens is yes, it's going to mutate, and we're going to get into what's called free radicals, and free radicals are what technically mutate the cell, but it literally takes my DNA. So inside my cell I've got DNA helix, right? That DNA tells that cell what it's going to become. You're a skin cell, or you're a bone cell, or whatever. That free radical goes in and maybe knocks off an A or a G or a T. What are the four letters? Yeah, AG knocks one of them off, and now that cell goes, oh crap, what am I supposed to be? So it doesn't know, so then it just starts, it says, I'm a cell, and I'm going to replicate, but I'm replicating at a pace that I can't control because I don't know what I'm supposed to be. And that's where that comes from.
So then why, when we're using radiation to like kill cancer cells, why doesn't it cause mutations on the cells around it?
It probably does, but it kills them fast enough that mutation can't be expressed. Does that make sense? So what they do is they're just trying to kill it. They're also killing other cells, which is why they're really careful about that. Because if I kill all the other cells, you're eventually going to die anyway, right? But I want to kill enough of the cancer cells that I can go in and cut that what's left out without doing too much damage to all the other cells that are around it. Does that make sense?
Yeah.
Yes.
It also kind of depends on like how it mutates your DNA though. So like if it just changes the letter, all right, whatever. If it changes like we talked about this maybe by the way. Anyway, but like you have your sequence of DNA. If it just knocks one out and it totally shifts it, that will like change it way more than if you just have it like replaced.
Gotcha.
And also we have like backups of a lot of our different cells. So like unless you have like.
So you'd have to get that one and the backup.
Yeah.
Which obviously happens because you look at the cancer rates. I mean, it's kind of crazy. Yeah.
So wait, why wouldn't you stop like cell replication rather than like going in and just trying to like kill all the cells? Or maybe like if you catch it early enough, could you like stop like the cell replication instead of like waiting?
Ooh. I'm not a biology guy. I don't know.
There's not really anything you can do to control cell replication.
Yeah, because that's the problem is once you've mutated that cell, we don't have any control of what it does. And we really don't know how it's been mutated. You know what I mean? And a lot of times they replicate with no purpose, and they seem to replicate fast for some reason. I don't know why that is. But it's crazy how fast sometimes they replicate. What?
Maybe stem cells could do something.
Maybe, yeah. But then you get into a whole nother controversy there, you know. So, all right, now we need to talk. Holy cow. Where did that go? But that was a great discussion, was it not?
Oh, yeah.
We do need to know this. You've got to know this term. We can't go on. You got to know PET scan. It is the only scan that actually uses radiation. An MRI is not radiation. A CAT scan is not radiation. An X-ray is not radiation. Because to truly be radiation, it's got to come from radioactive decay, which means I've got to have a radioactive isotope emitting particles or gamma rays. A PET scan is it, and it's called positron emission tomography. Now notice it's tomography, not topography. Topography is a map term, right? Topographic map shows the elevations or something, right? This is tomography. Positron, which makes sense. We got positrons, right? Positron emission tomography. That is the only scan that uses radiation. And I had never heard about it until I taught this class. Anybody in here ever got a PET scan?
My grandpa had one.
Really? What for?
He had a cancer like in his neck.
Oh, okay. Okay, but yo.
So a PET scan is only to detect cancer then?
No, I did not say that. It's the only thing that uses radiation. And in his situation, they use it to detect cancer.
Well,
Okay.
It was like they'd done a biopsy on it and they wanted to see like where it was.
Okay. So it must be a way to view it. Yes.
Wouldn't that be kind of dangerous?
Which is why all those other scans don't what?
Use radiation.
Don't use radiation. It's because of the danger factor of it. Yeah. Okay. Alrighty. Time is yours. Use it wisely.
Hey Denton, so I have to like leave for our basketball game like right after school. Is it okay if I use our work time to like go get ready right now? And I will.
So you're
work
saying,
out.
can you go get ready right now? Is that what you're asking me?
Yeah.
Sure.
Okay, thank you.
Yeah, whatever you gotta do. I mean, you look ready to me, but
I have to do my hair and makeup, so I have to put my hair in a high pony and I have to put on eyeshadow and eyelashes.
oh, I was just giving you crap. You're fine.
Thanks.
There's a video
Do you have a charger for a Chromebook by chance?
I have a flat one.
Yeah, that's what
Yeah.
that's right.
Bring about me Subway.
Have to say. Yes, the Steelers re-signed the Big Ben.
Wait, actually? To who? Oh, re-signed. I thought, yeah. Hey, that's good.